Alright, chemistry and water. So technically, I'm not supposed to do this because we skip over this in biology lectures. But I'm gonna do so because I think that the property of water is amazing, and the properties of water are amazing, and we wouldn't be alive without water. So this one goes really not. It doesn't go in depth, but it covers various topics on the surface, which can be a little bit tricky because for me at least, I want to understand how everything works before I understand the qualities of it. For example, like when I was first learning about biomacromolecules, um, researching them in my biology textbook, some things were just like I didn't really get it. So, like for example, um, I was like, well, where do the like how do these hydrocarbons link up so much? Where do they come from? And it's there's so many questions. And in fact, when we were doing something like polar coordinates, some things don't really make sense. You're just supposed to accept it as it is. But I guess that would make things quite a bit more difficult. But yeah. So first we have to go over atoms and molecules. So why study chemistry? All living things are made from atoms, stardust. Now I guess that would be a broad position because they're saying that all the atoms in your body are the same atoms that can be found in stardust. I think that stardust was made popular by um, I forgot the name, but it was a scientist. I think it might have been Richard Dawkins who essentially who to coin the name Stardust. I know it's been made popular by like Neil deGrasse Tyson and such. So that's what that means. All that means is that we're atoms just like the stars. And some even posit that the uh, the stardust came together, and over time we evolved into creatures from that same stardust. So that means we are literally stardust itself, and that's what my textbook kind of says. So life emerges from chemical interactions. That's pretty simple. That's pretty easy to understand. For example, um, when you eat a iron supplement, it's usually ferrous sulfate, um, and that's your body's water breaks that apart because um, it's an it's an ion which allows you to gain nutrients. So essentially, life emerges from chemical interactions every single day. Photosynthesis, cellular respiration, all that stuff. Biology is equal to chemistry applied to life. And I kind of find this interesting because if anybody's taking calculus, people say that physics is f of x, chemistry is f prime of x, and biology is f double prime of x. Simply saying that chemistry is applied physics and biology is applied chemistry. Now, some people take that the other way around, where they say biology is actually the first science because we're all alive. But simply put, biology is just applied chemistry. Um, so, what are atoms and molecules? Well, atoms are fundamental building blocks of matter. Um, Democritus, he first found the idea or posited the idea that we're made of in the or in separate in unsplittable particles. In fact, he says atomos, which means indivisible. So there are 3 points. They're made of protons, neutrons, and electrons. So note that we simplify them to plus one and electrons minus one. But my textbook didn't do this. And I think the reason they didn't do this is because they didn't want you to attribute a numerical value to the thing. So an electron's charge is negative 1.6 times 10 to the negative 19th, and a proton's charge is 1.6 times 10 to the 19th. But simply put, they cancel each other out in ratios of 1. So usually when we talk about elements and we say that it has a plus 2 charge, that actually means a plus 3.2 times 10 to the 16th charge, or 10 to the 19th charge, 10 to the negative 19th charge. So it's really just sign convention, and we're doing it in ratios. So that's what it is. Molecules, two or more atoms bonded together. So that could be oxygen gas, hydrogen gas. Note that here I only use diatomic molecules, but theoretically a molecule is just any two atoms bonded together. Diatomic just means two of the same atoms bonded together. Um, but it can be any two atoms. It can be carbonate, CO3, water, H2O. So this is a water molecule. Now, compound is a little bit more specific, and it's two or more different atoms bonded. So all compounds are molecules, but not all molecules are compounds. So we have water and carbon dioxide here. The subatomic particles, protons positive charge determine the element. So there's something. So we're not going to get into splitting of the atoms or quantum physics, but essentially, the protons will always determine the element. For example, hydrogen is 1, carbon is 6, oxygen is how did I not know this? Oxygen is 9. No, oxygen is how did I forget this? Um, Oxygen is 8, phosphorus is 15, neon is 10, helium is 2. So that's all those things. So essentially, when someone gives you the number of protons, you're able to determine the element just like that. Well, obviously, if you have a periodic table with you, neutrons are no charge, but they add mass, and in fact, neutrons and protons weigh the same. So that's something interesting for you. Electrons have a negative charge, and they're involved in bonding. Um, so remember, opposite charges attract, so protons and electrons will be very, very useful for bonding later on when we get to that. So atomic number is the number of protons. Again, defines element. So if I say this element has 4 protons, you're able to pick up on what it is right away. So yeah. Mass number is just the proton plus neutrons because those are the only ones that actually contribute to the mass. Protons actually weigh 1 Dalton, and I'm not too sure what that is in grams. But we just use 1 for simplicity, and I guess John Dalton coined it, so yeah. Elements cannot be broken down by normal chemical means, so that's why I said we're not going to get into quantum physics or quantum, oh, sorry. We're not going to get into fission or fusion. So the same number of protons equals same element. So again, that's what I meant when given the protons, you can just say what the number is. So isotopes are different because they have a different number of neutrons. So they have same charge but different mass because again, the proton determines the elements. So they have the same amount of protons but different amount of neutrons. Now the interesting thing here is that in nature, everything comes in a different amount of neutrons. Carbon comes with a different amount of neutrons. Phosphorus comes with a different amount of neutrons. Therefore, we have to use an atomic mass average. But again, that's not really too important right now, unless you're actually taking chemistry. This is just biology mixed with chemistry. So yeah, radioisotopes are unstable isotopes that decay, emit energy, and become different elements. So for example, I'm a photographer, and in old photography lens, they used to have thorium in the lens, but thorium is radioactive and decays. So yeah, it's pretty interesting. Valence electrons and reactivity. Valence electrons equals outer shell electrons. So that essentially means, see, like, I don't know, because they give this information to you, but you guys don't even know about shells yet. Essentially, it's the electrons on the outermost layer. So for example, well, I'm gonna use just a simplified model, the model that most people are familiar with. If these are all the electrons at the end are called the valence electrons, simply because they're the ones involved in bonding. Now, electrons actually do not look like this in real life. In fact, they use probability densities and stuff for that. So this is just a simple idea to show you that only electrons are on the outside, and that's what they mean by outer shell. So here the valence electrons would be 4. Now atoms on a full shell, which is the octet rule. Now the octet rule is weird because it doesn't apply to everything. It only applies to, I don't know if it's majority, but it applies to a lot of elements. And essentially it means that electrons want to gain a full octet, or a full octet, which means a full valence shell with 8 electrons. But obviously you have helium, which only has 1 s orbital, which means that it only forms a duet. So it's interesting things like that, and this determines chemical behavior. So ions are cations and anions, essentially meaning, again, remember the proton number does not change, or the protons do not change. So if it's positive, that means it's losing an electron, and if it's negative, it's gaining an electron. So these are the types of chemical bonds. Covalent bonds are share electrons. Now, nonpolar means equal sharing, and polar means unequal sharing, partial dipoles. So that goes into Vespert theory, and unfortunately that is gen chemistry, gen inorganic chemistry. So I'm not going to explain that too. I'm not going to explain that at all. Or I guess a little bit here. Um, there are different bonding angles and bonding types, such that certain elements, like this AB5 molecule here, or AB4 molecule here, um, will become a tetrahedral shape, which means that they share the electrons evenly because all of them are dispersed evenly. Now, there's something called electronegativity, which essentially means how strong an atom wants an electron, or it pulls on an electron. So you can use the Linus Pauling's electronegativity scale, where fluorine is a 4 and cesium is a zero point 0.7. And essentially, if one atom pulls on a specific atom's electrons more than the rest, then it will create a dipole. And water is actually a famous one for dipole simply because of its structure. Now, water is a bent molecule, and I'm not going to explain why again, because it would simply be outside the scope of our class. Now, this is what water looks like, and the reason is because there's lone pairs, but we're not going to get into that. So oxygen is pulling all the electrons here, which gives here a negative charge and proton a slight positive charge. That's why water's bonding is so strong, because another oxygen atom is going to come here and be attracted to this positive bond right there. Simple stuff. Ionic bonds are essentially bonds where there's a transfer of electrons, but once the transfer occurs, the strong enough um, electrostatic attraction between the positive and the negative ends come together and hold them there. So, for example, when water comes along, or actually, we shouldn't use water, like sodium chloride, which is table salt. A sodium's going to come next to a chloride and pull, or chlorine's going to pull an electron off the sodium. But once it pulls the electron off, they're so opposite in charge that they're going to just want to stick together. And that's essentially what that is. And it forms a crystal lattice. So, but we'll get to that a little later if we ever do. But in fact, like, I don't even know how teachers expect you to know this without actually reading chemistry, I guess. Because we jump to biology or biomacromolecules, a little bit of organic chemistry next lesson, and I don't know how they expect you to know this, but whatever. Van der Waals interactions are something with, so it's you have to know a little bit about electrons for this. Electrons don't stay still. They're not the model that you see. In fact, electrons have something called a probability region, where there are certain areas that they like to hang out, and they always move. So when they're moving, the electrons can go on one side of the atom or the other side of the atom, and because the electron's charge is always moving, it creates these positive temporary partial charges, uh, which means it goes and it bonds with the positive charges of other van der Waals molecules or other molecules that are having these electrons move around. So includes dipole-dipole and ion-dipole interactions. So this applies to everything. Every molecule has van der Waals interactions because every molecule doesn't have electrons just sitting in one place. So these are the major elements of life. How I like to memorize it is SHNOPS, which is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. But I don't know why they did SHANSP, but I guess you can memorize it the way you want to. So yeah. Why water is special? Polar molecule forms hydrogen bonds. Hydrogen bonds are just the same thing as dipoles, where one thing pulls harder. One atom pulls hard on other atoms, causing a imbalance of sharing electrons. The difference here, though, is that hydrogen is really, really weak, or really weak electronegatively. And what happens is the charge becomes so polar that this bonds become so strong. That's why, although hydrogen bonding is a form of dipole bonding, hydrogen bonding gets its own special name because it's so strong. I mean, that's pretty cool, isn't it? Note that hydrogen it only works when hydrogen is bonded to oxygen, nitrogen, and fluorine. So yeah, functions of water. It's an excellent solvent for polar/ionic substances. So if you drop salt into water, the the water will separate the salt. Note that like dissolves like, so water will dissolve ionic molecules. It's an excellent solvent for polar slash ionic. Oh, I already said that. High heat capacity. Um, if you're on fire, you should put water on yourself because that water will absorb the heat just like that. It's a high heat capacity essentially means that it takes a lot of energy to raise water 1 degree Celsius. So that's what it is. It enables cohesion and adhesion. So I can give you a few examples. For example, when you know what? Let me think of a better example. There's some weird things when you pour. Like, have you ever tried pouring something pouring like a drink, and the drink somehow gets stuck to the bottom of the container? Well, um, that's because when the water starts moving, some of the water gets stuck to the cup, and since that water that's stuck on the cup sticks to other water molecules, it creates kind of like a chain. That's also why when you see after it's rained and you look at leaves, there's water droplets all on the leaves that are forming this bead-like structure, and that's just because water is holding all those molecules together in a tightly packed spherical shape. So that's pretty interesting. Water sticks to water is essentially what it means. Adhesion is water sticks to other surfaces. Um, so for capillary action, where water climbs up plant stems, um, that's what adhesion is great for. Now let's go over the pH scale, and I love the pH scale because um, it is the hardest chapter in college chemistry, from what I've heard. But I thought it was pretty fun, and um, everyone knows about acids because they're in so many movies and stuff like that. So we have a scale from 1 to 14 basic. It uses a logarithmic scale, which is equal to unit 10 times change. Again, I still don't know like how they expect you to know this because they didn't even give you the formula of pH. pH is the negative log of hydronium ions or hydrogen ions, and that essentially corresponds to how acidic it is. The greater it is, the greater the amount of hydrogen ions, the smaller the pH is because taking the log of a very small number gives you a a small, very small um, negative or very large negative uh, reciprocal exponent. But if you get larger, um, if it becomes larger and closer to 1, then the scale becomes that the output of the logarithmic function would go to 1 or -1 in this case. So neutral is pH 7, but no, this is only at a certain temperature. So again, like there's just some weird things going on here, but fortunately, you only need to know the facts, I guess. So just make sure to know that. I don't really think you even need to know about this logarithmic scale because I don't think they're gonna ask you about that. But yeah, I mean it's pretty relevant to what we'll be studying in biology for the most part. So there's that. Diffusion is movement from high concentration to low concentration. So this is primarily focused on movement across membranes, but it can be used from anything. For example, if you fill a room with a gas, and then you open the door, all the gas is not going to stay there. Um, and I guess that is a consequence of, I can kind of apply it to thermodynamics, but that's just a consequence of statistics. It's more likely for that gas to leave the room. So that's the logic behind there. So it's affected by temperature, size, and charge. So yeah, osmosis is diffusion of water. Water moves from low solute to high solute. So kind of like the same thing as diffusion, except it requires a semi-permeable membrane and is in a solution. So like that door analogy I used before, just think about so many ions packed in a solution, and once you open that door, they want to move to the other side. And that's why we talk about semi-permeable membranes, which essentially means that it allows one side to pass those ions through. Now the tonicity is a little bit different as well. Hypotonic just means it's low solute. Isotonic means it's equal solute on both sides, and hypertonic means it's high solute. So transport mechanism. There's facilitated transfer, which are protein channels, high to low concentration, no adenosine triphosphate, and active transport is low to high concentration, requires adenosine triphosphate, and ion pumps. So calcium ion and a potassium ion right there. These are endocytosis and exocytosis. Endocytosis is where materials enter the cell. Exocytosis is when materials exit the cell. And pinocytosis is cell drinking. Um, Pino equals liquid. And phagocytosis is cell eating. Phago equals solid. So those are just the processes of the organic cells. And that's it for chemistry and water. Um, I will make a macromolecules soon, uh, but I haven't made the slides, so